This is Expert TA number 9, kinetic energy and angular momentum. This is problem number 4. Suppose a 210 kilogram motorcycle is heading towards a hill at a speed of 37 meters per second. The two wheels weigh 12 kilograms each and are each annular rings with the inner radius of 0.280 meters and an outer radius of 0.330 meters. So we've got our variables here. The mass is 210, blah, 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 blah. Part A says, how much can it coast up the hill if you neglect friction? So how high can it go? So we're going to start out with the moment of inertia is equal to 1/2 m, and this is normally r squared because there's two wheels, we have two radiuses. We're going to do r1 squared plus r2 squared, and we have our omega is equal to velocity over the radius, just to keep. And this is a conservation of energy problem, so we're going to have energy initial equals energy final. Start off with 1/2 m velocity initial squared because our motorcycle is already moving, plus 2 times 1/2 moment of inertia omega squared, and that is going to be equal to mgh because this is the h that we're looking for, and when it gets to the top of the hill it's only going to have this potential gravitational energy. So 1/2 mvi plus 2 times 1/2 iw omega, not w, equals mgh. This 2 and the 1/2 are going to cancel out. So we're going to have 1/2 m velocity initial plus, now we're going to have to put in our moment of inertia equation, which we have up here. So plus 1/2 m times r1 squared plus r2 squared, and our omega, which we have here, times velocity over radius. Both of these are squared because our omega is squared right there. It's equal to mgh. Now we're going to fill in all our variables. So 1/2 times the mass of the motorcycle, which is 210, times the velocity, which is 37, this is all given, plus 1/2 times the mass. And this is where many people can get confused. You are not going to use the mass of the motorcycle. You instead are going to use the mass of the wheels, which each weigh 12 kilograms, times 12 times radius 1, which was 0.28 squared plus 0.33 squared times 37 squared divided by the radius 0.33 squared equals, our mass is 210 times gravity 9.8, and our final variable h. So if you plug this all into our calculator, we will get a final h is equal to 76.11 meters. So 76.11 meters. If our motorcycle was coasting up a hill, this is how far it would make it. Now part B is asking how much energy is lost to friction if the motorcycle only gains altitude of 38 meters before coming to rest. So this is another conservation of energy problem. So we're going to start off with energy initial equals energy final. And then we start with our initial energy is 1/2 mv squared plus moment of inertia times theta equals mgh, and here we are actually going to keep the force of friction minus the force of friction. So because we're looking for the force of friction, obviously we have force of friction, we want to isolate it, is equal to mgh, put this right here, minus 1/2 mv squared minus moment of inertia times omega. This is because we basically took the force of friction and put it over here and then brought everything from this side over to the right. So if we put in our variables, we have force of friction is equal to mass 210 times 9.8 for gravity times 38 because it's how high we went in meters, minus 1/2 the mass, again 210 times our velocity 37 squared, minus so I did this work eventually, but this answer that we got from up here is equal to 1,427.476. And we have that the force of friction is eventually equal to negative 79,668.476. But because we are looking for the positive force, even though it is negative because it is going in the opposite direction of our hill, so more like that on our hill, and we're going like that, we're going to enter into our exportier 79,668.776 newtons, and that is our force of friction. We only made it up 38 meters. So this is the final work for exportier number 9 on exportier unit 9, problem number 4 on kinetic energy, rotational and angular momentum.